All right, let's talk about something I'm sure we've all seen. You know that moment a word problem goes up on the board and suddenly you can just see students' eyes start to glaze over? Well, that's exactly the challenge we're tackling today: how to crack the code of one variable equations for eighth graders.
So, how do you empower a student to look at a complicated story and pull out a simple, solvable equation? That's what we're going to dig into. It's about building that bridge between a real world scenario and the math. And this isn't just some random skill, it's a huge part of the Texas state standards, the TEKS. And let's be honest, it's a hurdle where a lot of students, and hey, even teachers, can get pretty stuck.
Okay, so here's our game plan. We're going to start with the challenge itself. Then we'll look at how to actually write and solve these problems. From there, we'll decode the most common mistakes students are making. And we'll wrap it all up with a playbook of strategies you can take right into your classroom.
Okay, let's dive right in. And this is the big picture, right? A student's journey in algebra, maybe even their whole future in higher math, can seriously hinge on this one thing: their ability to translate real situations into the language of math.
I mean, at its core, what we're really doing is teaching students to be like mathematical translators, turning words and situations into algebra. And this is so much more than a school skill. It's a foundational skill for logical thinking and problem solving in, well, pretty much any field.
Okay, so let's get into the nitty gritty. We're going to start by unpacking our first key standard. And this one's all about representation. It focuses on just getting the problem down on paper.
So the standard is pretty clear. Students are expected to write one variable equations or inequalities with variables on both sides that represent problems. And the crucial point here is that before they solve anything, they first have to be able to set up the problem correctly. It all starts there.
Okay, check this out. This is a classic moving truck problem, and it's a perfect real-world example. It asks students to compare two different pricing models. And to even get started, they have to put on their detective hats, right? They need to figure out the constants, those are the flat fees, and then the variable rates that change with every mile. But here's the reality check. Only 58% of students could actually set up the inequality correctly for this problem. Just let that sink in for a second. That means more than 40% of students were lost before they even got to the solving part. That shows a huge gap in this foundational skill. And hey, it's not always about moving trucks. This problem shows a totally different angle on the same standard. Here, students have to translate geometric properties, the sides of a rectangle, into an algebraic inequality. So we've gone from a rate problem to a geometry problem, but the core skill is exactly the same. Can you represent the situation with math? All right, so we've seen how problems get written down. Now let's move on to the next piece of the puzzle, actually solving them. Okay, so this standard says students are expected to model and solve these equations. And I really want you to notice that word model. It's not just about abstract calculation, it's about understanding what the calculation actually represents. And as an educator, this is where the magic really happens. We can start with concrete models, like these algebra tiles you see here, to build a solid visual foundation before we jump to the abstract stuff. It makes all the difference. Now, what's really interesting about this next one, a word problem about hot wings, is how it combines both of the skills we've talked about. First, you have to formulate the equation, 8x plus 4 equals 10x plus 2.8e, and then you have to solve for x. And the results here are absolutely staggering. Only 1 in 4 students could correctly figure out the cost of one hot wing. That means a full 75% of students got this wrong. It really highlights the major challenge we're up against when we ask them to put these skills together. So what's going on here? Why is this so tough? Let's take a look at the most common errors students are making. Okay, these patterns pop up again and again. Things like treating unlike terms as like terms, combining 2x and 3 to get 5x, or confusing inverse operations, especially when negative signs are involved. Not doing the same thing to both sides of the equation is a big one, and of course, forgetting to divide by the coefficient at the very end. These point to some really specific misunderstandings we need to address. This triangle problem is a classic trap. The perimeter is 17x, so the equation should be 15 plus 15 plus 7x equals 17x. But a super common mistake is to just mash together the constant 30 with the variable term 7x. Okay, now let's look at a problem that adds another layer of complexity: fractions. Ugh, right. This is where multiple errors can just stack up on top of each other. And yeah, the data totally confirms this. Less than half of the students, only 47%, could navigate through all those fractions and inverse operations to find the right answer. All right, understanding the problem is step one. So now, let's talk solutions. Let's build our educator's playbook with some actionable strategies for the classroom. The path to understanding really does have some clear steps. First, you start with the concrete, physical objects, like algebra tiles. Then you connect that to the symbolic, explicitly linking what you're doing with your hands to the steps in the written equation. And only then, once that foundation is solid, do you introduce the abstract stuff with rational numbers and more complex problems. It's a process.
Yeah, and this quote really says it all. As students begin to associate the representation and manipulation of the concrete objects to the symbolic solving of the equation, then the abstract solving can be introduced. That's the key takeaway, right? That bridge between the physical and the abstract has to be built intentionally. It doesn't just appear. So, what's the big goal here? It's to help students see that any action has to be replicated on both sides of that equal sign to maintain equality. Ultimately, whether you're using tiles or symbols, the fundamental concept we're teaching is just balance.
So here's a final thought to leave you with. What's one activity you could use, maybe even this week, to help your students physically feel the concept of keeping an equation in balance? Because when we focus on that idea of balance, we really do transform a bunch of confusing rules into something that feels intuitive and powerful. And that's the real goal, is